skipping Wolff-Dietrich reduction. Skipping it as in, we're skipping those slides, I'm not going over the mechanism, and therefore you guys do not need to know that mechanism. Okay. So, we start with lots of colors. And as always, our carbonyl carbon is gonna go ahead and be green. Okay. R prime, because why not? And then, yeah. So, boron. And then basically, they do this, Na plus, basically, and then, okay, yeah, and then a minus, I don't know. You could also just do around here because it's not, they're necessarily going to hang out right next to one of the hydrogens, but I don't know. I don't care how you draw this, like, I don't care where you put this guy. Honestly, we could do this and I'd be happy because, like, I mean, the ion's going to dissociate anyway. It's going to go piece out somewhere else. Okay, so all 4 hydrogens are red because any of them could be a nucleophile because this can reduce 4 times. So we are going to do an attack, and in this case, the only time we're going to take an arrow from a hydrogen to elsewhere. Now, can I start my arrow directly on the hydrogen? No, because the only time I have to start my arrow with where the electrons are, right? And hydrogen, I mean, it's got an S1, and there's no P1, it's just S1. And then you'd have to have an S2, and then a P2 to actually get to an octet, right? So it's got an S1, its valence shell is 2, and that is a full valence shell. So the only electrons it has, it's bonding with, so we're going to take the arrow from there and attack here. This is, reduction is the only time we're allowed to do this. Yeah. Fourth, we get that. And with reduction, you're going to, with reduction, you're going to more often make negative charges, at least on, your carbonyl oxygens and such.
Why is it still double bonded?
It is not. Good call. See, you guys are going to be so practiced at finding your own mistakes when you go, when you take your exams and quizzes, because you get so much practice finding mine. That goes to here. We have, we're going to keep calling these minus, yeah, and then just, because that's where those guys hang out. And this hydrogen, R prime, R, the new hydrogen that actually, I mean, if we really want it, we can do. No, we always do it this way. Hydrogen came with its own electrons, but I'm not going to draw them red because then I should have been doing that from the start. Because nucleophiles always bring their own electrons, right? Yes? No?
So the oxygen attacks the boron after it loses the first hydrogen?
Yeah, so basically you just sort of, like, they don't actually have a, Like, I really don't like this,
Yeah.
because that's how they have, like, these are straight from your slides.
Yeah.
So like they draw these two, and then they put that there, and I don't know, I don't like it. I would rather just do O minus, honestly.
Because doesn't the oxygen get a hydrogen after this?
Yes, it does. So maybe those just, I don't know, that just, it doesn't, like, I don't know, I don't like it, and I will not count you wrong if you just draw this like this. Prime, not minus. If you just draw it like that, I think that that is fully acceptable.
And then what?
Particularly because there should never be a bond that like breaks or forms in a mechanism that you don't have arrows for. Like that just breaks the rules. I don't like it.
So
So
then should that, if you were to draw it the second way, would it just be then plus BH3 without a, like,
Yeah, then
lone
you just
pair,
have
and then you would just do a nucleus.
BH3 and
Is it a nucleus?
there'd be Na plus hanging out there, but so this this boron doesn't have a charge, right? But also this is, there's no lone pair because those electrons got taken,
Right.
like and taken. And boron is cool with this. It's one of the very few atoms that's just like, hey, you know what? Sometimes if I have 6 valence electrons, I'll just live with it. It's fine. I won't have a charge, but I'll just live like this. It's okay. And that's because boron comes with, what, 3 valence electrons? Okay. Yeah. I always have to look at a periodic table to double check. But yeah, boron comes with 3 valence electrons, so if you make 3 bonds and just leave an empty orbital, then it's happy enough. So, yeah. I mean, usually you probably have to have some sort of ion or counter ion or something. I don't know, but it does that sometimes. So you can do this and it's fine. And you don't have to like do an additional step with the boron bonds to this, because like whatever, it's just hanging out there for a little bit of stability. You know? We can do this. Actually, you know what? I'm gonna do that. I'm gonna draw it the way I wanna do it, because you will get to see it the other way in your notes, and then we can see our nice, and you have a question, sorry.
Oh, I was gonna say, why does the sodium not attack the oxygen if it's positively charged and the boron doesn't have a charge?
Oh, so,
Or I mean, the oxygen attacks the sodium instead of the boron.
sodium, you know how, we have talked about, let's see, did I talk about percent ionic character of bonds? Did you guys, I don't think I did. Did you guys hear about that in last? No, I think that was a concept that I meant to hit in chapter 15. But it's a concept that Nerul talked about in different words. So, you know how he was like, hey, if you've got,
Oh, is it like how much percentage of an S versus a P orbital, like,
yeah, like,
are in the hybridization?
when you do hybridization, you've got like percent S character, percent P character, and sp3 is less S character, less like fraction S character than sp2. This is percent ionic character, so it's whenever you've got like a carbon or something and a metal, and it's like, this guy wants to do an ionic bond, and this guy doesn't want to do that. No, we're not gonna do that aside. I mean, basically, the only thing I can think of is that, like, I don't know, so, we very specifically, in chapter 15, we make some very specific, like, oh, we have an organometallic compound, and like, the bond that we draw from the carbon to the metal, like that counts as a bond. That counts as like one of carbon's 4 bonds and stuff. Most of the time when we've got metals like hanging out with things, it doesn't, the bonds to metals don't really count as one of that atom's bonds. So like whenever, so sodium, like if it's gonna be complexed by stuff, it's gonna be like, I don't know, something like that. Like it's, I always draw these because I don't want us to mistake it for a sigma bond, because it wouldn't make this not negatively charged. It's just sort of, usually it's, yeah,
It
what,
doesn't wanna like share them, it just wants to.
yeah, it's like a security blanket. Like it's not sharing them in a whole bond. It's just like, oh, okay, if you guys will hang out here with your lone pairs, that's cool. And it doesn't even have to be negatively charged, because your lithium is stabilized by ethers in it gets complex by ethers. So like this guy doesn't get a charge because it's not sharing them that much. It's just sort of letting you hang out near its stability. Does that make sense? Okay. Yeah. Long story short, metals are weird. I don't like them. Okay. Yeah, I hate this. I really hate this. Okay. This mechanism, they gave us our mechanism, like our step here. They want to say that this is so the negative charge is over here, H3Na+, and then I got rid of that because I assumed we were doing more steps with that, but their mechanism then takes this and goes, okay, then you do a workup. You take, you take this guy, this doing this. Fine, I'll draw the dumb boron thing. Okay, this isn't even a full mechanism. I'm not gonna like, the only thing I can really have you draw, or like the only mechanism adjacent thing I could have you do with this is like, show me the original nucleophilic attack. That's like the only thing I can do here. Because the next mechanistic step is, all right, do a water workup, and then you get and this guy is not red, right? Because all of those red ones, they bring their electrons with them. They are hydrides. So if it came from there, it would have brought electrons with it. This guy already has electrons. I mean, we could draw like this, or we could go, that's hanging out on its own, and this is doing that. Regardless, we just need a proton, right? So that guy came from water in the workup step. That's their mechanism. I got all excited to do a mechanism because I had that on here, but yeah, it's not really the whole mechanism. Okay. What time is it? 35. Okay, LiAlH4 reduction. We are going to finish this chapter. We're going to finish this chapter tomorrow if it kills us. And yeah, that's what we're doing. Tomorrow we are finishing this chapter. That's just how it's going to be. Hopefully we'll start chapter 17. But, okay, LiAlH4, that is another, basically a hydride. This is going to react violently with water, alcohols, and other protic solvents. So like, this guy doesn't really seem to freak out if it's around like an acid. Like like, you're gonna kill it with water, right? You're gonna be able to take one of these and one of those and just, I think you kill it with water. No, sorry, NaBH4 is stable in water. You can do this in aqueous solution. So, these guys, this is a way to make hydride, where hydride is a good nucleophile, but not a good base. Usually, base and nucleophile, like if you're one, you're the other, or if you're nucleophile, you're a good base too, right? This one is a much more aggressive nucleophile, and because of that, it is also a very good base. So LiALH4, you are not going to put this in aqueous alcohol or any alcohol because it will be real violent. You can do this in ether or THF, just stuff that's not protic. And this, is gonna do the same thing, it seems. Oh, these guys are different. These guys are different once we get to carboxylic acid derivatives. That's what it is. Yes.
So if you put in like extra of this, would it then like eventually reduce that OH group that it made?
I think no. I think actually no, and honestly, I want to just make sure I'm not lying to you. LAH, reduce alcohol. Nope. All right, cool. So neither of these guys reduce alcohol. When we're talking about a ketone or an aldehyde, these guys are interchangeable, NADH4 and LAH, except with LAH, you can't let there be any water or alcohol or anything protic in there, which also means you can't have like an acidic hydrogen on your thing. I mean, it would use some of it up, but you've got more moles of reduction than you need, but also like it would just be violent, so like, don't do it. These won't always be same. Yeah, okay. Catalytic reduction, that's gonna be similar to what you guys did with double bonds, where you go, here, have a bunch of H2 gas, let's just fill a pressure flask with a bunch of H2 gas, put a metal in there, usually platinum, but you can do like nickel, and there you go, you get reduction. That will reduce these guys to alcohols as well, whether you use platinum or nickel, but, oh yeah, it looks like it doesn't even matter. I think both, yeah, because platinum would totally do it, so if even nickel will do it. These guys will leave your alcohols alone, or it'll turn this into an alcohol and leave it, but if you've got a double or triple bond, it kills that. So, all right. I should have actually set an alarm for the end of class, because I was like waiting for that to go off, and then I was like, oh no, I actually have to check the time. Okay. Yeah. We'll talk about selective reduction, and we will speed through this stuff tomorrow. And when I try to talk about non-lecture things, stop me and tell me we got lecture to get through, because we talked about plenty of business things. Your homework assignment, I put it up in an announcement, because that was the easiest way to do it quickly, but there will eventually be a place where you can attach whatever kinds of files that you need. So, yeah. And those are